Hello everyone, and we have another session of the course Line Commutated and PWM Rectifiers, and today we will talk about the simulation. I will show you a demonstration of a MATLAB simulation of VSC. Okay, so basically we are in this part in module B of the course. We have already covered the design example, and today I'll show you how we can actually simulate this in a software. I'll go through the whole simulation step by step. So why do we use these kind of simulation tools? Is that they are very useful nowadays. It is actually quite expensive to always build the hardware first and test it. Rather than that, throughout all of power electronics, generally we model our systems at first in a software, and then we run the simulations. We see the results, we fine tune what are the changes needed, and then after we are satisfied with all the simulation results, then we go with the experimental implementation. This is a very standard way of development which is used both in academia as well as in industry. In order to do this MATLAB simulation, I will take the same example as we had taken previously as part of when I was talking about the Bode plot. Okay, and you can see here some of the parameters like this S. We are basically simulating a grid connected VSC with a grid voltage of 400 volt and the total power being 50 kVA. We will do the simulation in the per unit system, and so we will define these V base, I base like this, which I have already talked before, but these are again shown in the slide here. Now we have taken here about 4% filtered impedance, and with an L filter of this 0.41 millihenry, and in per unit it is 0.04 per unit, and coil Q of the coil is 30, and so this is like per unit resistance of the filter, and the DC bus is 600 volt, and the switching frequency we have taken 20 kilohertz. Now with this I will when I will do the simulation, initially I will work with a 50 kVA, but later you will see I will change the rating to 10 kVA, and then you can see that the system automatically will adjust itself. Okay, and this is one of the advantages of having a per unit system. Okay, now just to give you a overview of what we are going to do during simulation, at first you will see that the VSC is initially not connected to the grid. So basically there is a voltage source converter, there is a filter, and there is a grid, right? And in between there is a breaker. Okay, and that breaker is initially open. Okay, and so we will start the VSC, and it will be initially in open loop. Okay, and during this time what happens is the PLL of the VSC gets synchronized with the grid voltage. So we give time for that PLL to get synchronized. So it is as if like a synchronous machine. When you connect to the infinite bus bar, at first the synchronous machine is excited from a prime mover and the voltage is generated, but the breaker is open. Okay, in a similar way, the VSC is fed from the PLL, and the DC bus, here we have assumed the DC bus to be constant and it has already been pre-charged. In practical scenarios, sometimes we require special technique to pre-charge the capacitor. Otherwise, if you turn on the breaker, the DC bus, if it is fully de-energized, the capacitor, then a huge inrush current will happen and the breaker will open once more. So then you cannot actually run the system. So it is important that for this kind of grid connected VSC, it is important to pre-charge the capacitors. Okay, so the capacitors are pre-charged, or the DC link is pre-charged, and the PLL is working so that the voltage source converter starts to produce a voltage. However, it is not connected to the grid. At t equal to 0.2 second, the breaker is closed with P star equal to Q star equal to 0, which means at t equal to 0.2 seconds, we are closing the breaker, and we will give a P star and Q star equal to 0, which means the VSC is not exchanging any active or reactive power with the grid. Okay, so it is just as if it is like floating. The delta angle between these two AC sources is 0. Okay, so after it settles at t equal to 0.4 seconds, we see that we will give the first P star equal to 1 per unit. So in this case, we will give about 50 kilowatt, and Q star is equal to 0. And you will see that how nicely the currents will get settled, the controllers will work, and it will immediately be able to deliver this 1 per unit power to the grid. At t equal to 0.6 seconds, we will make P star equal to -1 per unit. So it is a full reversal of the active power, but we will keep Q star equal to 0. As I have repeatedly told you, with a grid current, with a grid voltage oriented vector control, we can independently control P and Q. Here you can see how we are controlling that. At t equal to 0.8 second, we will give under this condition of -1 per unit of P star and Q star equal to 0, we will give a grid voltage sag of 20%. Okay. Yeah, so then we will see if the sag is 20%, what will happen is the current will increase. Remember, the voltage source converter here is working with a P and Q reference. It does not care what is the grid voltage. So if the grid voltage goes down, the current which is fed or injected into the grid, that will increase by the same amount so as to keep the P constant. That is what the the VSC is supposed to act. So in spite of this grid voltage sag, the current, the power will remain the same as before, and so therefore the current will increase, and we will see that happening at t equal to 0.8 second. Then at t equal to 1 second, we will remove the grid voltage sag. Okay, and the converter will again come back to its original working condition of P star -1 per unit and Q star 0. And at t equal to 1.2 seconds, we will give a P star of -1 per unit and Q star of 0.5 per unit. So here now we are changing the Q star, and we will see its effect. So this is like what we are going to do. So if you keep this thing in mind, then you will be able to understand the simulation. Now I have now connected to my desktop PC. So at first I will show you the simulation running. Okay. So here I don't know whether you are able to see, the font size is not so big. Okay, here you can see how the code looks like. So here first we introduce this frequency, and FC is the switching frequency. We can change this one. VDC is 600, VGrid is 400, S is 50,000. Okay, I'll change it to 10 kVA for demonstration purpose. And then we have V base, I base, Z base, and all these has been initialized. And then we have also this LF, ZF, and all. Okay, so this program is quite generic, so we can actually also simulate a STATCOM with this. But in this simulation, which I am going to show now, we have a steep DC link. So we can also put a DC link capacitor here. And then here we have been, this code is commented right now, but here you can see how the PODE plot has been generated. And I told you that we use the loop gain, okay, G and GC, and then you can have an asymptotic Bode plot like this. Okay, and so if I just run this one, okay, you can see what happens. This is the asymptotic Bode plot of the loop gain, and this is exactly what I had shown in the as part of the simulation. So there was a pole at origin, so we have used a PI controller, and so there was one pole at origin, and then there was a second pole here and a 0 here. Okay, this we have explained in the last class. Now let me, okay, so this I'll close, and here now let me open the simulation. Okay, so I will go through this block by block, but at first I would like you to see the waveforms first. So let me run this simulation, and I will first explain to you how the waveforms look like. So there is one block here where I am collecting all the waveforms and putting it into an oscilloscope. Okay, so let us first do this step by step. What are these waveforms? You can see here where my pointer is now. The first one is this modulating signal, and we are basically using space vector PWM. Okay, so this is like the waveform or modulating waveform for space vector PWM. Next one is grid current, actual grid current. Next is the reference and actual power. Okay, so whatever is P star and whatever actual power is flowing, this is plotted here. Next is the grid voltage and grid current, and here this blue one which you are seeing now, this is the grid voltage. The light blue one, or later you will see when the grid voltage when the grid current starts to flow, you will see a grid current coming here. This is the actual reactive power, VAR. Okay, then you have IGD and IGQ in per unit, and IGD controller reference and the controller output here you can see, and VConv D. So these are the two per unit output of VConv D. So this is going to the Parkes transformation matrix so as to get VA star, VB star, and VC star. Right. So as I told you initially, up to t equal to 0.2 second, which means here t equal to 0.2 second is here. Up to t equal to 0.2 second, the breaker is open, and during this time the modulating signals have been formed. However, the controller is disabled during this time. This is important. The controller should be disabled, okay, so that it does not produce any output. So the input is 0 and it should not produce any output, right? So now at t equal to 0.2 second, I have closed the breaker, okay, and as I close the breaker, you can see there is some inrush current. You can see here there is some inrush current, which is of not very high magnitude, but there is something flowing here. Okay, I have closed the breaker. The modulating waveform is there and the voltages are getting generated. Okay, so therefore at this condition the P star and Q star are both 0. So which means the current is 0, almost 0. Here you can see the current is almost 0, because the voltage source converter and the grid, they have been synchronized. Okay, the voltage is getting generated. Okay, Vcon D and Vcon Q, the voltage is getting generated at the voltage source converter output. There is a Vcon D, which means the VA star, VB star and VC star, they are getting generated here. Okay, after Park's transformation, but no current is flowing. So the two systems are floating at this point of time. So now let us continue and see what happens at t equal to 0.4 second. We will give a active power reference of 1 per unit. So let us continue with that. Okay, and at 0.4 second we will give a 1 per unit active power reference. So now just let it settle a little bit. Now here, okay, now you see at t equal to 0.4 second, you can see this pink waveform here. This is the current, and the blue, the dark blue is the voltage, right? So here you can see that the reference and actual active power, you can see the blue one here is the reference active power and the pink one is the actual power. Okay, and this value is 50 kilowatt. Okay, this is 1 per unit. I have given a 1 per unit. Okay, corresponding to that, about the peak current was 100 ampere, just above 100 ampere. So this is being seen here. Okay, and here you can see IGD and IGQ. This IGD has gone to 1 per unit. Okay, because I have given P star equal to 1 per unit, but IGQ is 0 here. So therefore the reactive power is almost 0 here, the actual reactive power which is flowing. One interesting thing here is the output of the controller. Okay, I will later zoom in, but what you can see here is that the IGD controller momentarily hits saturation. Okay, the IG, because the input to the IGD controller is a 1 per unit. Okay, and therefore momentarily the controller output hits the saturation and then comes out. Okay, because momentarily the error is very large, so the controller hits the saturation or the maximum output. But then when the error starts to fall, you can see here the error is going down. Okay, the error becomes almost 0, very close to 0, and so therefore it goes out and again comes back to the normal position. Okay, and here you can see the VGD and VGQ which is needed for the modulating signals. So here you can observe that the voltage source converter is actually pretty fast. Okay, if you properly tune using suppose a Bode plot technique or some other technique, then the response of this converter is quite fast. Okay, so let me continue with the simulation, and we will wait till t equal to 0.6 seconds. So which means it will come here. Okay, t equal to 0.6 second, it will come here, where I will give a p star of -1 per unit. You see here, I have given a p star of -1 per unit. You can see here, let me pause again. Okay, here you see this was p star equal to +1 per unit, and then it goes to -1 per unit here. Okay, how do you know? Because you see here the grid voltage and the grid current have now become 180-degree opposite. Okay, so this means a reversal of power. But on the other hand, you can see the Q is 0. It is still 0. I have not given any command to Q. IGD, you can see it is going from +1 to -1. IGQ remaining 0. Okay, IGD has gone from +1 to -1. And of course, the IGD controller goes from +1 to -1 here. Okay, very quick transition. Right. So let me continue with this, and at t equal to I think sometime later we will have the grid voltage sag. Okay, I think around t equal to 0.8 seconds here we will have the sag. Yes, now you see there is a sag. Okay, let me just stop here. Okay, here you see I have not shown the actual, so here you can see this is the actual voltage. You see here the blue one was the grid voltage, right? The grid voltage actually had a sag. I think this sag is 30%, most probably. I have to check my code. I will show you the code. Probably this is 30% sag from the magnitude, it seems to me. Anyway, it will also work with 20% sag also. So this is like some sag is there in the voltage, but you can see here the current. Okay, the current is also shown here. The current is immediately increased in value, right? Okay, and and this is also evident because you can see IGD has gone to -1.3 or -1.4, something like that. If it is a 30% sag, it should go to 30% more. Okay, right? Because we are feeding the power at unity power factor. So yeah, this is how the system will behave when it is given a sag. Again, because of the fast action of the controller, the system is not only stable, but it can quickly track any disturbance which is happening. It can quickly overcome any disturbance that is happening in the grid. Let me continue with the simulation, and at I think t equal to 0.9 second here, the sag is removed, right? So we'll stop here again. So this is t equal to 0.9. Okay, so here the sag is removed, and so here you can see the current has come back again here to its normal value, right? And here also IGD comes back to the normal value. Okay, so again let me continue with the simulation, and after some time, I think, yes, now here I think at t equal to 1, okay, we have a q star which we will give. Okay, so just I will so at t equal to 1 seconds, right, at t equal to 1 second, so probably there is a mistake in the slide. I have written t equal to 1.2 second. It should be t equal to 1 second. At t equal to 1 second, I have given a Q star equal to 2.5. I mean 50%, 0.5 per unit, 2.5 kVr. Okay, this command has been given here. Okay, at t equal to 1 seconds, and so it is nicely tracking. Q star is tracking. The P star and P remains as it is. You can see there is no change in the P star, which was -1 per unit or -50 kilowatt. What happens when you increase the Q star is that, suppose I zoom in here, you can see at t equal to 1 second, the current actually increases in magnitude, and the current here, you can see the current here was perfectly out of phase with the voltage because Q star was 0 at this point. But now, after some time, around this point, like 1.02, 1.03 seconds, after the transition has been done, you can see here that there is a phase lag. You can see the lag there is a phase shift between the current and the voltage, indicating that a reactive power has started to flow. You can see here that IGD and IGQ, IGD maintains -1, but IGQ goes to 0.5 because Q star has been given 0.5 per unit, and this is the actual Q star. Okay, actual Q, this is about 2.5 kVr. Okay, and these are some of the other transients. Okay, here is the zoomed version of the modulating signals, and here also you can see how the current waveforms look like. Okay, so let me again get the full picture once more, and I want you to see the zoomed in versions of these areas. So this is the area where, if you can recall, at t equal to 0.4 seconds, we had given a P star of 1 per unit, and then initially the current was 0, and then it immediately jumped to about 100 ampere. Okay, and this is what I wanted to show you here in this curve, is that this IGT controller reference and output. So the IGT controller, it immediately hits the saturation. Whenever this P star was given a 1 per unit command, the IGT controller immediately hit the saturation, but then it came back. It went out of that because the error was made 0. Okay, so it came out, and this is how it will look like, okay, at the steady state. Okay, so let me again zoom into some other area, for example, +1 to -1 per unit. So here I zoom in this portion. You can see here the current. Okay, this current was in phase here with the voltage. Grid voltage and grid current are in phase, but grid voltage and grid current here becomes out of phase, right? So this is another thing that you can observe, right? Yeah, and of course you have the Q star command, which I have already shown you this way. Okay, so this is how the simulation will run, okay, with different things. You can also have more waveforms that you can capture and can observe. One of the things that I would like to do now is that I will change the converter rating to 10 kVA. So let me go to this MATLAB file, and here at the top I will change to, see, instead of 50 kVA, now I will change it to 10 kVA. Okay, right, because the whole simulation is on per unit, This is advantageous. Now the plot slightly changes based on the values that we have calculated, and these steps I have already shown to you in the lecture. Okay, so let me do this, and then let me again. So now, since this is 10 kVA, you can see the currents, the base value of the I base. If you see here, I can just type here, I base is now 20 ampere. Okay, so which means peak of the current will be roughly 20 ampere. Earlier it was 100 ampere. Okay, so suppose if I take this one to 50 kVA and run it, then this I base was around 102 ampere, but now I change this to, of course it will go by 5 times less. Okay, and so the I base now is 20 point something, right? So let me, with this thing, let me go back and run the simulation once more. Okay, so let the simulation run, and by the time I will again show you the waveforms. It starts again with the same strategy. Okay, and here you can see initially the converter is booting, kind of like coming up. Okay, we can say in computer language booting up, something like that, just for a fun. I mean, not exactly booting, but it is now so initial part, the breaker is open, and now here I have turned on the breaker. Okay, t equal to 0.2 seconds, the breaker is on, there is an inrush. Okay, now let us continue, and at t equal to 0.4, I think here around this point there will be a P star equal to 1 per unit, but now 1 per unit is 10 kVA, 10 kilowatt. Yes, now you see, let me zoom in and pause. Okay, now here you see this current is no longer 100 ampere, this current is now 20 ampere, and it is nicely getting tracked, right? You can see here it is nicely getting tracked, and here also the current is in phase. If I zoom in here, the grid voltage and the grid current are nicely getting tracked, but of course the current magnitude has gone down by 5 times. Okay, so this is how. So but IGD again is 1 per unit. Okay, because this is a per unit system, it is still tracking with 1 per unit, but our per unit system has the base values have changed now. So let us continue, and you can see exactly the simulation will continue the way I have shown you in the previous simulation. Okay, and here you can find out that again the P star will go from you can see here it is 10 kVA now. P star is 10 kVA, 10 kilowatt, and from 10 kilowatt it is going to minus 10 kilowatt. Okay, of course Q star is almost 0. There is a slight reactive power flowing. This is because of the filter. The filter is taking a little bit of reactive power. Okay, so then again there is a sag. You can see during that sag, yes, the sag is 30%. Actually now we can the sag is almost like 30%. We'll see that much, how much is the sag I have given in the simulation. So this is how it will be looking like, and then you have at t equal to 1 seconds the Q star has been given, and you can see here it is 0.5 per unit. So which means now it is 5000 var or 5 kVA. So again, let me show you in this fashion the whole picture. And so now you understand that what is the benefit and why did we do a per unit model. In a per unit model, there is little effort while running, because it is all these things are in per unit. Okay, so this is something which I wanted to talk. Now let me stop here and let me again now look into the block diagrams. Okay, what is inside the simulation block diagram? Now let me show you the model in more details, how I have developed it in MATLAB, and how this whole thing is running. Okay, so here you can see the first block here, which is here you can see this is the converter formation. Okay, so this is where I am making the converter. In this subsystem, I am interfacing the converter with the grid, and we have the filter here, and here we have the grid. Okay, inside this block we have the grid, and here in this block we have the controller, and this block here is where we can see all the waveforms. Okay, so this is the easiest block. So let me first show you. It is very simple. I mean, all the variables that I have collected in several places, all these variables I am putting it into this scope, and this was the scope I was showing you earlier. Other types of variables can also, you can put it. For example, you can see the pole voltages. I have not shown you this one because it makes it unnecessarily okay, so I think no, yeah, so this is the pole voltage waveform. Okay, you can see here the pole voltage. You can see this is a series of PWM pulses. Okay, all these VAO, VBO and VCO. I have not shown you this one, okay, because at that switching frequency this will not be evident. Okay, fine. So this is the first block here. Okay, this block is the right, this is the simplest block. The next one is this one, the grid formation block. Okay, what is there inside this block? So here you can see how we have developed the grid. Okay, so here you see this is the 50 Hertz, this is the frequency, and then we get the omega, and this is the clock which gives you here omega t. And omega t, we have used this floor function in the blocks, so that omega t, otherwise omega t will be continuously increasing as the simulation is ongoing, but we want that omega t should be always between 0 and 2 pi, and that is why we have used this float block. Okay, and so omega t increases from 0, it hits 2 pi and then again comes back to 0. This is how it is done. Okay, so the float function is basically that lower limit and then only takes the integral part. Okay, the integral part is taken away, the fractional part is taken. So this is very common in MATLAB. Now this is where the omega t comes, and this omega t is here moving from 0 to 2 pi, and then we have this 3 phase. I am making the 3 phase so as to make omega t and omega t minus 2 pi by 3 and omega t minus 4 pi by 3, and then I am using a cosine function to make the grid, and then multiplying with this quantity so this is the per phase. Okay, so this we have done, and so this will form VAG, VBG and VCG. Okay, now as you can see here, I have also introduced a sag. As I was telling you, the sag here is 0.7, so which means there is a 30% sag. Okay, and you can see here how this is implemented. So there is a switch here, and initially most of the time this lower line is activated, but under certain condition, okay, the upper line is activated, and so we will get 0.7 of the V grid. When will it activate? You see here, at t equal to 0.8 seconds the thing gets activated, and at t equal to 0.9 second the sag is deactivated. Okay, so by using these two step functions we can actually control this switch here so as to allow a 1 per unit voltage or a 0.7 per unit voltage to come on the grid or to appear as the grid voltage. Okay, so this is how we can do a grid voltage including the sag. So let us now, so we have covered this one and we have now covered the grid formation. Next is the converter formation. So let us look into the converter formation. The converter formation is basically very simple. You can see here, this is basically the converter here. Okay, what is done here? The converter is nothing but, since this is a stiff DC link, the converter is VDC by 2 and minus VDC by 2. Okay, so it gets two of these voltages depending on what is the sine triangle PWM we are using. Depending on the PWM that we are using space vector PWM. So this is your VA star, VA reference, VB reference, VC reference, VA star, VB star, VC star. This will be space vector PWM, and this will be compared with the triangle here. Okay, and depending on that, the upper switch or the lower switch will get activated, and so this VDC by 2 or minus VDC by 2, this comes on the VAO. VAO is the pole voltage of the converter. Okay, now you can actually find out what is the DC link current. You can find out here. If we use a STATCOM, then this will be used. Okay, the IDC we can use at it, but right now we have disabled this one. Okay, we are not using this one, but you can do to find out how much is the DC link current. Okay, so this is the converter formation. Now what is this converter and grid voltage? Converter and grid, how do they interact? Now here you see this VAO, VBO and VCO, these are the pole voltages. From the pole voltages you can get the converter phase voltages. Okay, so what is the equation here? If you remember, in one of the lectures we had said it was 2/3 VAO minus 1/3 VBO minus 1/3 VCO, and that is used here. Okay, this is the formula that we have used. Okay, so this is that one, and then you get the converter phase voltage. That converter phase voltage minus the grid phase voltage gives you Ri plus L di dt across the filter, and this is how the filter is implemented. Okay, so here is the voltage VA, the difference of the grid voltage and the converter voltage, and then minus Ri comes here, and then 1 by L, here is the 1 by L, LF is the filter inductance, and integration of that gives you the current. That is the current which is flowing from the converter. Okay, if the breaker is open, Okay, you can see here I have written close contactor. As long as the contactor is not closed, IA value will be 0. Okay, when the contactor closes, it gets the correct value which flows. Okay, so this, therefore here this block is like interacting with the grid and the converter. Now the last block is the controller here. This is the most important block. What is there here? Okay, now here there are, you can see several smaller blocks. This is where you actually get your triangles. So we are generating the triangles here. You can see here, if you see, this is the with FC. FC is, I think we have used probably 20 kilohertz or 10 kilohertz, some value like that. Okay, that I have used, which is written in the M file in the MATLAB. Now there is also this block PLL. Okay, so what is there in the PLL? Okay, it checks the voltages here, the grid voltage, and divides by V base, and then it, so I have used the PLL of MATLAB, but you can also develop the PLL of yourself. Okay, it is again a closed loop control with a DQ transformation inside. Okay, it is very easy to develop it, but I did not have the time to do it, so I quickly took this PLL from MATLAB. Okay, but it is very easy to develop this PLL block by yourself. And then you get the frequency and the omega t. As I told you, we will then, the PLL actually tracks the grid voltage, and therefore this theta is basically the one which is tracking the grid voltage. Okay, here is the theta, and of course you get the omega value, okay, based on the frequency. So the PLL output in this MATLAB block is the frequency and the theta. Okay, basically omega t, and that frequency, and this gets, you will also get the omega. This omega is needed for the feed forward terms. Okay, so this is the PLL here. Then we have this one, the current sensing. Okay, this is basically the current sensing. Okay, you have the IA, IB, IC, divide by I base, and okay, this is ABC to current sensing as well as ABC to DQ transformation. So you have this current which is sensed and divided by I base, and then we are doing here the parts transformation, and therefore we get IGD and IGQ. Okay, here one thing I have done is that I have used a small low pass filter after the sensing. This is usually done. Okay, when you sense the current, in order to get rid of the switching frequency components or noises, a small low pass filter is used either in the hardware or in the software, or in some cases in both the places. Okay, a small low pass filter. So this low pass filter is implemented in MATLAB using a transfer function. Okay, it's just a small low pass filter. This should be sufficient. And so this is the IABC to IGD IGQ. Okay, so we get the grid currents. What is there inside this one? Again, the grid voltages. Since the grid voltages in this case is, we have assumed to be very good quality grid voltage, I did not use a low pass filter here. Okay, and I have straightly taken here to the parts transformation and got the VGD and VGQ. Okay, so this block here, check DQ power, this was just for my own calculation, I was doing it, this is not important, right? Now let us come to this main thing. This is the main controller. What is the input to this controller? You can see here the input to this controller is P star and Q star. Okay, these are the two inputs, Pref and Qref here. Okay, and what is the output? Output of the controller is VA star, VB star, VC star. Three references coming here. Okay, so these are the input and output of this controller. Now here you can see the P star is changing. These blocks here, you can understand that the P star and Q star are changing. As I told you, we are changing P star from 1, -1, like that. Okay, so suppose here you see at t equal to 0.4, I have given 1 per unit here. Okay, but again at t equal to 0.6, I have given a -2. Why have I given -2? Because I am going from +1 to -1, right? So therefore, that is how you can actually have all these step inputs, okay, at different time instants, and then you can add them and get this Pref, right? This multiplying factor is used because there was a per unit initially. You can see why that 1.5 in the slides I have told that there was a 3/2 factor, and that is why this 1.5 comes here. Okay, now then this Pref is becoming the IGD ref calculator, right? Because this P star becomes IG star when you divide by 2/3 of VGD. Here you can see here 2/3 of VGD, you divide it. Okay, this comes from the equations, and then you get IGD star. Here you get IGD star. Okay, so this output here is IGD star. Exactly in a similar fashion, you have the Q star here 1.5, and then you have the IGQ star. Okay, you get an IGQ star here, right? So this then is the IGD star and IGQ star here. Now comes the controller or compensator. What is there here? Suppose I take the IGD controller. Here you see this is the input. Now as I told you initially, when the breaker is open, I have disabled the controller, and this disabling happens through this. You can see here, as long as the contactor is open, we should not actually start the controller because it will immediately go into saturation. In fact, it will go into deep saturation. So in order to prevent, then we must have an anti-wind up and something like that. So what I have done in this simulation is that I have disabled the controller initially. Okay, but as soon as the contactor is closed, then this gets the input. So this is where the controller input comes. Of course, then you have the IGD star here coming on this line, IGD star here, and IGD actual. The error comes here, and then it is going to the Kp and Ki multipliers. Remember here, you must have saturator blocks, okay, at the output of both the integrator as well as the output of the total controller. The saturator block is a very important block. Okay, you can see here 1 and -1, I have kept the limits. The saturator block is very important because it actually keeps your output under your control. Okay, you know that the output cannot go beyond 1 or -1. Okay, and it is always a very good idea to actually limit the output of your controller. Okay, and so this is the Kp and Ki, and then this is a saturator, and this is the controller output. Pretty simple implementation, which you can also do. In a similar way, if you see the Q controller, inside the Q controller, it's the same thing. Okay, you get the IGQ reference, actual IGQ, KI, KP you can use, and then you get the output here from the controller. Okay, again you have to use those saturated blocks here. Okay, once you have got these two elements, then you have the feed forward terms which you add. So feed forward here, as I told you, we have used that omega times L, omega into L into IGQ and VGD. Again I have used a saturated block here just to make sure that things do not get out of my control. In a similar way, here also you have this feed forward terms which is shown here. Okay, once you have done these two, then you add them, and then you can get these quantities here. This is the V con D, VD star and VQ star. Okay, these are the two quantities, VD star and VQ star, which we obtain here. Again, this is an overkill, but I have tried again. I have inserted one more saturator. I was just making sure that the outputs of these quantities we don't want an over modulation. Okay, so I kept it inside the upper and lower limits. Okay, there is no harm in putting this saturated block additionals. So here there is this VD star, and here comes the VQ star, and the V0 is 0, and so you have a DQ to ABC transformation here. So what is inside here is nothing but a simple inverse Parkes transformation matrix, and this will give you here the VA star, VB star and VC star, right? Okay, now here, because I have used space vector PWM, I have given this maximum value to be 1.154. okay, so it should not, it should go beyond 1 here. Okay, but you can use sine PWM also. Okay, now what is there inside this space vector PWM block? It is just as I told you, here comes those sine waves, 3 sine waves, and I have just used a max, min and minus 0.5. That means minus half of max plus min, and then I get a new set of modulating waveforms here which is suitable for space vector PWM. Okay, I do not have to do any sector calculation, timing calculation, nothing. So it is just a simple line of code. Okay, max, min and minus half of that, and then I get VA star, VB star and VC star, right here, and this VA star, VB star, VC star will go to here you can see VA ref, VB ref and VC ref, which will be compared with the triangles, and VAO, VBO, the switches will be turned on and off, and you get the pole voltages from the converter. Okay, so this is how the whole system works, and I have shown you step by step all the blocks, and I think you should, so the output is something like this as we started, and I think with this introduction of the models, you can develop these models on your own. Okay, so you should make these models. So some people ask me that you do not use any of the Simulink power system block set or something like that, which is given in MATLAB. We do not recommend it, and we recommend that you should use the basic blocks of MATLAB. Okay, because this GUI is very useful, because you do not need to memorize a lot of code, syntax, etc. You can using the graphical interface, you can quickly connect blocks, multiply, divide, and all those stuff. You can quickly do it, and it will be very useful. But on the other hand, if you rely too much on advanced blocks which are given in MATLAB, like sim power system and all, you actually lose control over what you are doing. Okay, and so we do not want to lose that control. And so I recommend that you use simple blocks or basic blocks of MATLAB, like I have shown you, and you can implement more or less almost everything. If you want to have a deadband, you can implement it. If you want to have delays, you can also implement it. So many things can be done just by using those basic blocks. You have to write some additional logic or take some small blocks and can make some logic. So hopefully by this introduction to the simulation, I hope you can develop codes and models on yourself, and this is something which all students who want to work on it should develop on their own. Okay, so if you take a ready-made code from someone, it is not advisable. Okay, it is not advisable to take a ready-made code from someone, because it is important for you to learn how you can do these things. And I have shown you all the blocks that my model runs, and it should be easy for you to now develop your own model and run it. Okay, with that we conclude this session.